So don't.
No more
So
family talk.
what's that?
No more family talk.
No more family talk. Keep it PG, please, and super serial. Um, so I have a few things that I want to go over today, but it's not going to be super time consuming. So I wanted to open up the floor and see how everybody's feeling, and if everybody's had a chance to at least look at the homework and feels comfortable with it, and then just open the floor for any questions on anything we've gone over so far. I'm here for you. Don't everybody speak up at once.
I'm feeling pretty good.
Yeah?
That's all I got.
I'm glad you're feeling good. So everybody's like just super happy with how everything's working, and they figured out all the homework and they know how to program everything and they have no questions at all.
Programming wise, I'm gonna probably be rolling around and tussling with it for a little while longer, but I think
Okay.
given the videos and everything and the support, it'd be pretty easy to figure it out. You know?
Sure.
But, yeah.
Is there anything specific you're butting your head on?
Probably just getting used to the getting used to how logic runs itself. You know.
Yeah.
That's I think the biggest hurdle for me is just sort of understanding it.
Yeah, it's a little weird. It's different than other programming. It's kind of interesting because that whole it just keeps it rescans and re-executes every couple milliseconds, right? And so like compared to writing structured text like in MATLAB or whatever we use at Davis, it's going to be Python now, where you're kind of writing a script that runs once, right? Here you're thinking this is running continuously. You got to be thinking about what happens in these different states and how's this stuff going to blow itself up if it just keeps running indefinitely, right? So that can be a little challenging if you're not used to it. Did everybody get a chance to watch that 8-minute video I made about programming a touchscreen?
Yeah.
Yeah? Good. That's a plus. So hopefully that homework should be fairly straightforward. I left it open. Sorry?
You want us to record of our work and submit our video?
Yeah. So that recording, I don't want you to record a 1-hour video of you programming stuff. I want you to make just a quick clip, just demoing how your panel functions in that simulation mode, right? Just so that way, I mean, I will open everybody's file and check it out and see if there's anything I can give meaningful feedback on. But really, like, if you have a functioning HMI, it should be self-evident from you clicking around in simulation mode and showing what it does, right? So that's why I just asked. I'm trying to put more time into this class, but at the same time, like it's kind of hard to spend more than maybe 10 to 15 minutes grading each thing. So I'm asking you to help me.
Is a video the only submission, or is a video in what we did on that? See more.
Yeah, please upload the file if you can. If you're able to save the file off, please send me that as well. If you can't because you're on the VM, then just do the video. And I know that's not ideal, and I'm sorry, but that's what we're working with this quarter until they open up that software to be free.
This is for homework 5, right?
This is the make some HMI screens homework.
Okay, with the Seymour stuff. Okay, I think I'm a little bit behind.
That's all right.
There.
I'm gonna share my screen real quick. So, I've been super happy with like the level of participation and the level of effort that everybody's putting into these assignments. So, I really appreciate you guys taking this seriously. It's really nice from my end because I'm putting a lot of time into this, and so seeing you guys really take it on and actually show interest in this is huge because it's rewarding for me. So I really appreciate that. And you guys are doing awesome. So coming up, we have this assignment to go watch some YouTube videos. I found this channel called Learn Engineering that's just, they make really high quality videos. The average length is between 5 and 10 minutes. So let me just pop that open. I just asked you guys to watch this one on how AC induction motors work, which is the motor that we're working with from an electrical standpoint. And then this second one is how transistors work and how they function and how they're made. So it's basically what they cover in material science can just condense down into 5 minutes. So that's a really good video. So I think that one's like due at the end of the quarter, but I encourage you to watch that sooner rather than later. There's the optional countdown lights assignment, and then there's the program HMI screens assignment. So I'm gonna open up one more after this, which is gonna be open-ended. And so the one that I hope y'all will do is make a puzzle. So basically, in the integration between the HMI and the PLC, like make a couple screens and stuff, and make a puzzle to where like all the lights are on the panel, and you have to like click through and figure out how to turn them off. And there's like conditionals, or they flash in a certain something like that, where it's like a little puzzle game that that you got to figure out. I think that would be really cool. And then the other thing is just going to be PID loops. And so I don't think I'm going to assign that out as like a project for each person. I think that's just something that we're going to work on together going forward, starting on Wednesday. And maybe we'll even talk about that a little more today. So that's what we got. That's our scope for the rest of the quarter. I'm gonna turn it back over and see, does anybody have any concerns or anything they'd like to do? Are you guys interested in maybe looking at something else in AutoCAD that we didn't really cover, or exploring something in more detail, or anything along those lines? Okay. Fair enough. Well, at any point, if you have some input, if there's something you want to do, something you want to look at, please let me know. And you can just email me, and I'm more than happy to put in some time ahead of time if it's not something that I can just talk about right off the bat. Look into it and talk about it in a meaningful way in this class. So give me 1 second. I'm gonna retool my cameras, and then we're gonna talk about a couple of concepts that have to do with sensors. You guys like my super high-tech camera setup? The great thing about this camera is that 50% of the time, it works 100% of the time.
Repeat that.
Oh, this camera. So like 50% of the time, it works 100% of the time.
Okay, I thought so.
It's the Panther.
Anchorman, got it.
Yeah. There we go. She's not working. Why is she not working? She was working this morning. Let me see if Zoom will read this actually. Come on. Okay, that's a problem. Okay, Zoom doesn't want to read this camera either. Gosh dang it. I apologize, guys. I fire this thing up every morning, and then there we go. Shabam. So yeah, for whatever reason, like somehow when it's like with the changing of the eventide, it just doesn't want to work when you first fire it up. So now she works. Okay, so the thing I want to talk about today has to do, or it has its roots in transistors, which I just talked about as one of those videos that I want you guys to watch. And so I apologize for doing this a little bit out of order, but hopefully when you go watch that video, this makes sense in context. And to be honest, you don't particularly need to know the nitty-gritty physics part about how a transistor works. But very briefly, the symbol for a transistor looks like, I'm going to draw it up here. They're drawn like this. Arrow in, arrow out. This is plus, this is minus. So that's the symbol for a transistor. And this is PNP configuration. Okay. And PNP means positive, negative, positive doping. So if you had a little sheet of silicon, the middle region would be negatively doped, and each side would be positively doped. They'll explain this in detail in the video, but this is how this is the important physics side of how this works. And so basically, when you have a field sensor device like we have, like this, why is this not? Bear with me. Like this fork sensor, one of the things that you have to take into account when you're wiring this up is this has a transistor inside of it that's either PNP or alternatively it's NPN, okay? And in industry, these will be referred to as sourcing or NPN is referred to as sinking. And so the way this is configured ultimately determines how your wiring for this sensor works. And it's really not that big a deal, but if you get it backwards, your input to your PLC won't work. And so this sensor takes, I have the manual in here. So this sensor has a 3-wire configuration. This is the manual. Focus. Right here. Focus right here. I know you can do it. So you can see here, they have a little wiring diagram in there for PNP or NPN. So why does this matter? Why are we talking about it? When you're wiring up input sensor to your PLC, you have your PLC card that looks like, so you just have your little input card. And for us, we have our C1 point, and this is where we're going to feed voltage to. And then you have your X1 through X4, your inputs, right? And so if you looked at the hardware manuals for our input cards, you'll notice that they all say syncing or sourcing. Okay, well, what does that mean? For sourcing, which is what we have, it means that you have to wire your 0-volt reference point into this common channel, and then you wire your sensor into the input, and then that sensor also gets it gets 24 volts and 0 volts. But basically, internally, this sensor has a switch, and when that switch closes, it puts 24 volts out on this line into the controller, and then that inside the controller, there's basically a switch that gets closed, and that that syncs down to your 0 volts, which is essentially your ground in this circuit, right? And so the sensor, your field device, is sourcing voltage into the input card. And so that's why PNP is called sourcing, because this sensor here is essentially acting as a switch on your source of voltage in this circuit. So alternatively, for a syncing configuration, if you had an NPN device, a syncing device, you would be wiring 24 volts into your input card, and then your switch on the sensor side would be your sync, and so voltage would flow into the card and then through the device, through your sensor. And so basically, when this sensor gets closed, it closes the circuit, and your voltage is sunk through the sensor. So another way of looking at this, so this what I just drew is how we would draw it on our panel drawings, right? The other way of looking at this is basically, if you want to just draw a simple circuit, you have your PLC, and then in series with that, you have your sensor. And this is just a simple circuit. And so this block right here, this sense block, is just a switch. Excuse me. And so in this diagram, your current is flowing this way. And so you're switching the source. So this would be PNP. And then for NPN, I'm just going to draw that as a switch. For NPN, your current is flowing this way. And so this is a sync, right? Because you're syncing the current out of the PLC and it's going this direction. So for us, this is important to know, because when you're buying hardware, you need to know, A, how are you going to wire up your PLC, and how are you going to make sure that your devices are going to signal properly. because if you have a PNP switch and you wire your device for NPN or syncing, then your input's not going to fire. You're not going to read an input from your sensor. And so this is just something to be aware of when you're putting together a system that has a lot of field devices, a lot of sensors. You're gonna need, more than likely, you should just budget to have one card configured for PNP and one card configured for NPN. That's like an ideal world, and where you can just take whatever type of device, because these sensors off the shelf, most of them are configured one way or the other. They have a single transistor in here that controls the firing of the output. And so you can't select that. That being said, there are some more expensive devices where you can select whether it's NPN or PNP. And it has the internal circuitry to adjust that with the flip of a switch. But for us, we have one or the other. For the other nice thing is, for us, if you open up the hardware, actually, you know what? I'm just going to do that. Let me switch the screen I'm sharing, and we're going to go check out the Automation Direct hardware pages.
What does PNP stand for? You said was the
So NPN and PNP it's actually comes from the way that transistors are doped. And so a transistor is like the fundamental component of semiconductors. So your CPU in any, like your cell phone or computer or whatever, has billions of transistors in it. And so what that is it's a treatment of silicone with either, I think it's germanium or phosphorus, I think, are the common dopants. Or sorry, boron and phosphorus, I think, in modern day. And so what they do is they actually basically impregnate the silicone with either boron or phosphorus, and it changes the properties of that material so that it conducts under certain conditions. So definitely go watch that video. But basically what they do is they have a positively doped and then a negatively doped. And this is physically like a sheet of silicone, and then a positively doped. And so what this does is it basically, you have a switching circuit on this side. And so this is called the gate. This is called the emitter.
You can't see what you're drawing.
Oh yeah, I got it. Sorry. Wrong screen. Thank you. Okay, so for doped silicone, you have your positive, your negative, and your positive region if it's PNP. And so this is the emitter, this is the gate, and this is the collector. And then you'll have basically a switching circuit on this side that controls the gate. And what happens is when this switching circuit closes, it will, let me see if I'm saying this right. It will draw electrons out of this region and create a small circuit. And then what happens is you have your primary circuit on this side. So let's say you have a light bulb, just because it's the easiest thing. And so when this switching circuit is closed, then it basically changes the electron configuration in this semiconductor and allows current to flow through this main circuit. And there's complex physics that you would study as an electrical engineer that are involved in this that I'm really not qualified to speak on. So I'm going to leave it at that. But basically, this transistor is essentially two diodes wired in series. Okay. And so if you remember, we talked about early on, diodes are directional. They only allow current flow in one direction, which is the direction that the arrow is pointing when you draw this. And so if you have this circuit where it's two diodes facing in opposite directions, essentially you cannot have current flow through here. And so what a transistor does is there's a lead coming off here that basically you can think. I think of it as like injecting current and inducing electron flow backwards through this diode. And so when you switch this gate, you'll get electron flow through this diode, and then it just automatically flows through this diode. And so it allows you to switch a circuit without having any moving parts. And so essentially this setup replaces a physical relay in your circuit. And it does it with complicated physics that were only really developed. I think the first working transistor was made in the, I want to say 50s by a guy named Jack Kilby. So Google that. That's really cool history to look up. He worked for TI, and he basically made a transistor when everybody else was on summer vacation. I digress. I can send you more info on that if you want. Again, I'm not an expert on the physics of semiconductors, so I'm not going to spend any more time talking out of school. But that PNP and NPN refers to the physical doping of the semiconductor inside your sensor. Okay, so if we go on Automation Direct and look up our Click PLC series, and look at DC inputs and outputs. This is this C008ND3. That's what we have. I want to pull up the spec sheet for this real quick. And if you look here, the inputs per module under the specs, it says sync source. Okay, so that means we can wire this for syncing, or we can wire this for sourcing. I.e., we can wire it NPN or PNP. We just got to know what we need and do it that way. And so if you look at the diagram over here on the left, you'll see it shows an equivalent circuit. So I'm gonna well, I don't think I need to redraw this at this point. I think y'all can. I've redrawn this equivalent enough times, and so you can see it's showing here on these inputs. You can have your power source in either polarity orientation, right? You can have the positive or negative end of your power source connected to that common C1 input point, right? And then you have all of your input devices, which are just shown as little switches here, wired in parallel off of that voltage source, and then wired into your inputs, your 1, 2, 3, 4 inputs. Okay. Now the cool thing about these modules is it has 8 inputs, but they're broken up into 2 groups of 4 off 2 common channels. So if I want 4 inputs to be PNP, I wire them PNP to that C1 input, and then on that same card, I can have 4 inputs that are NPN off the C2 input. So this is really nice. It's pretty cool that Automation Direct made their input modules this way, because with some other equipment vendors, you might have to buy the whole card as PNP, and you don't have the option to switch it to NPN, and all 8 inputs are one or the other. So in that sense, these Automation Direct cards are awesome because they give you a lot of flexibility in how you wire things. So not on the semiconductor part, because like I said, go watch the video I posted. It's really good. It's on Learn Engineering. But as far as the actual wiring for these sensors, is everybody pretty clear? Does that make sense?
Indeedicals.
Indeedicals. Awesome. Okay. So the second thing I want to talk about along these lines is just how the internal circuitry for this works. And so you have this second diagram here. Let's see how I'm gonna do this. Well, I'm going to redraw that diagram and talk about it because there's a few things that I think are good information to have. So sorry I can't show them side by side, but basically what you had is your power source wired to your input card. Okay, and this has a switch. So this is like a push button in the field, right? And you have your power source and it's wired to your input card. And so inside this card, you have a physical wire to a resistor. And then actually in between there, you have a capacitor and another resistor. Don't worry about that part. It's not really super relevant to the point I want to make, which is that inside this circuit here, you have two diodes wired in parallel with each other. In opposite directions, okay? And these are actually LEDs. Okay, so what does this configuration do when you have two diodes in parallel like this? In terms of circuitry. Come on, guys. Oh, we got a chat option. So we got a chat that says you can go either way. You absolutely can. All of you can go either way. But in terms of circuits, you can flow current in either direction. Exactly. So you can flow either way. And so what that means is that's where that NPN, PNP flexibility comes in, because you can wire your power source in either polarity, and this circuit will still be complete and have current flow through these diodes when you close this contact. Awesome. So these light up. Now, this is what they call optical, looks like I froze. Oh, I'm back. Okay, so this is what they call optical isolation. And so the value here is that you have these two LEDs. So when I close this circuit, this lights up, and this is inside the card itself where this is happening. These LEDs light up, and then on the other side of that, you have a, I think it's an optocoupler or a photoreceptor that's going to ground. And then let's see, and there's a resistor on that, and there's also, again, that side resistor and capacitor. Don't worry about that, it's not really relevant. And so this goes to an internal circuit, and so when these light up, this little opto, I forgot what it's called again. I just said it. Anyway, this is a light sensor. And so when light hits this thing, current flows through this circuit and basically gets read inside the PLC. And that's how it knows this input is engaged. So why is this useful? Why would you want to have optically isolated inputs on your PLC? Anybody? Think in terms of relays. What can you do with relays? What's the advantage that you get with a relay? Like the physical relays that we talked about before. Well, I'll tell you, it's that you have physical isolation of your two circuits. So what this means is inside the PLC here, you have this little internal circuit that's taking a physical input from the field that might have all kinds of nasty stuff going on. And it definitely has the potential to short, and it has the potential for somebody to like cross this with another circuit, a high voltage circuit or something, and short this out and explode stuff, right? And so what'll happen in that case is if you overload this circuit, this particular internal circuit on the input might get burned out, okay? Because it'll see a lot of current, but only this stuff will get fried right here. And the rest of the stuff will be fine on this end. And everything upstream of this, because it's physically isolated, doesn't get fried. And so if you have a 8-point card, you might fry one input, but the rest of them are fine. And you also don't fry the PLC that your card is connected to, because when you connect that card is now internally connected to the PLC on its internal circuitry. So basically, this just creates another layer of separation, another boundary between your physical input and your processor, your logic circuitry. So when I learned about that, I just thought it was super cool. It's an optical relay. Somebody in the or Mason in the chat just said it's an optical relay. And that's exactly it. So where conventional relays use an electromagnetic field to physically switch something, this is all done with light, and so it has no moving parts. So for one, it has longer longevity. 2, it has better response time, and 3, it creates that boundary layer, because you just have light. And it's pretty cool, dude. That's why I talked about this, because I just, when I learned about this, I was like, that's so freaking rad, dude. Like, that's just really, really creative, and it's a good thing to think about, if you're going into hardware design and that kind of thing, which I know as chemies we're probably not, but just the mindset when you're developing this of like, how do I create layers of security in here, right? Because on the field side over here in this circuit, you should have a fuse, right? More than likely, you're going to have, you're going to have somewhere in that circuit a fuse block. Blue screen. You're going to have a fuse block that'll blow if you overload your field side circuitry, right? But then an additional layer of protection comes inside your hardware itself. So we had a question: is there a larger possibility of the sensor misreading? Great question. I'm not a hardware expert on this stuff. I can't tell you for sure, but I don't believe so. So I'm pretty sure internally here, this is like inside of a plastic box that's sealed, and so you're not going to see like bleeding of outside light into this. And so, I can't tell you the statistics of like a misread on this versus a conventional physical relay, but I would guess actually this is probably more or less susceptible to false positives than a conventional relay. Because like a conventional electromechanical relay, if you are driving along and you drive past a big enough magnet, I mean, it's not going to happen, but if you drove past a magnetron or a magnetron was walked past your device, it would fire that relay internally, because it's a physical system. Whereas this, you actually need to get light in here for this sensor to read it. And so I think really the only way that would happen is if your component got physically damaged. And at that point, if it's broken enough for light to get in here, then it's already toast anyway. So good question. So those are the 2 things I really wanted to talk about. Syncing and sourcing, and then the optical isolation. Last little anecdote on syncing versus sourcing. I once bought a printer from a company that was getting installed on a production line, and I also bought a sensor from them to go with the printer. Same sales guy told the sales guy this sensor is going onto this printer. It's going to be the trigger for this printer, and I didn't do my due diligence specking out parts. I just told him, hey, this is the sensor I need, this model sensor for this printer, and he sent me a PNP sensor, and the printer was configured NPN. So out of the box, I was like, awesome. This is, thank you for checking on that for me, sales guy. So, lesson learned on my part, always check your bill of materials when you're designing something and speccing it out and building it. And then, verify with the sales guy that he's aware of this too, because your hardware just won't work if you don't get the wrong stuff. And so luckily in that instance, you could actually rewire the printer internally. It had some jumpers that you could change around to change the printer inputs to be PNP or NPN. So I was actually able to make it work, and I probably should have followed up with the sales guy and seen if he knew that or not. But it's just something to be aware of, that you got to make sure that all your hardware is going to integrate together when you're designing something in terms of the wiring. And then also, sales guys just want to sell you stuff. So you need to be educated on what you're buying and make sure it's spec'd out correctly. Clear as mud. Anybody have anything you want me to clarify on the sensors?
Why are physical relays even used? Because this thing sounds better. Is it just more expensive or something?
Versus transistors?
The optical thing.
Oh, the optocoupling?
Yeah.
Yeah, I mean, this is all semiconductor based. So I mean, pound for pound, semiconductors are cheaper because it's much smaller. But they're also, they may not be as robust in terms of like if you're in a heavy industrial setting where you have a lot of vibrations and stuff. The semiconductors need to be in more shockproof casing, so you get expense there. In terms of designing, a semiconductor fab is super expensive to run. Like a semiconductor foundry costs on the order of $1 billion a year to operate. And so there's an inherent cost in design where you're not just designing this piece, you're designing a silicon wafer that has as many of these pieces as you can jam in there, that then get etched on that wafer, and then they get cut up by a die cutter and sorter. And so there's all this inherent cost. And then along the lines, Mason just asked, is it harder to service and maintain an optical this opto-coupled relay? So this is going to be soldered. This optical connection is going to be soldered onto a circuit board, whereas an industrially available relay, which turns out I have one right here. Bear with me one second. Oy, that doesn't look good. There, that's better. So I just so happen to have a relay. So most modern industrial relays you'll have available come like this, where it's actually, this is your relay and this is your base. And so this is an 8-point socket, and you can see here there's 8 termination points. And so that way you can get different style of relays that all plug into this base socket. And so that kind of allows you a little bit of different flexibility how you wire this up. So to be honest, Andrew, more and more things are going towards semiconductor based integrated circuits. So, you know, the modern cars these days might have on the order of thousands of microprocessor integrated circuit devices, not microprocessors, but ICs and circuit boards that have semiconductors on them. Whereas, you know, 20 years ago, everything in your car was just pretty much relay based. So when you're doing manufacturing at scale, ultimately, yeah, semiconductors are usually more cost effective and in some ways more robust. But there's a much higher initial cost of investment to design those versus just, hey, make it all out of relays. And if you only have, you know, 5 or 10 control points, probably cheaper to just use relays. But again, it's all economies of scale.
Thank you.
Absolutely. Also, I'm not an expert on this, so you know, you can look into this more on your own. Fun fact: Matt Dara actually started his career at a company called NEC out in Roseville. That was a semiconductor foundry. That's now TSI. But if you're interested in he was an equipment engineer, so if you're interested in just asking about what that's like, he would be a good source too. Cool. So on Wednesday, we're going to talk about PID control loops a little bit. And then, did you guys find what we talked about today interesting? And would you be interested in talking a little bit more about sensor technology and how that works?
Yes, absolutely.
Yeah? Okay. Cool. So this summer, I interned at Eichleay with their instrumentation department, which was a really cool job. And I had some downtime and they had a huge resource library available. So I spent a ton of time reading up on like how pressure sensors work and all that stuff. So a lot of those resources are available in our drive actually, because they were public sources. So I'll put together some talks about a few common types of instruments that you'll see in industrial process engineering. So we'll talk about that a little bit, and then I'll point you to some further reading resources. I love this stuff. I just don't want to go too far off in the weeds if you guys aren't interested.
I'm just trying to learn everything you know, so just tell me everything.
Well, that won't be hard because I don't know much. Cool. All right. So that's the game plan. Anybody got anything else? All right. Well, I wish you luck with your further endeavors in programming HMI screens. I hope, well, hopefully you've started it already, and I hope that's enjoyable. The first time I got in there and figured out you could simulate this stuff, I just had a freaking field day because it's really nice. Like, you don't need any hardware, and you can fully program and test all your HMI screens without it. So it's a really nice software. I'm gonna stop the recording now.